Welcome everybody to creating a Firemonkey 3D application that'll run on Windows and Macintosh with C++ Builder. On my Windows machine, I've got the course book draft for lesson 7. So in the course book, we cover how to build 3D applications. We'll take a look at this nice math visualization application that Anders Olsen built for C++ Builder that runs on Windows and Macintosh using a T-mesh component to build a mathematical function visualization and to texture it with colors based on the value of y. A little bit of overview of the Firemonkey application, just there. The poster is available for download, and there's a link inside of the HD lesson and this lesson 7 to the nice big PDF file that you can print out on a big printer plotter, put up on the wall. Everything inherits from T-object and ultimately from T-FMX object. And we looked last time when we did HD applications in lesson 5, I think it was, yeah, about the 2D shapes of T-line, T-text, T-ellipse, T-circle, T-rectangle, and the styled controls for HD applications of T-edit, T-label, T-button, and such. This time we're going to focus on the 3D controls, and these 3D controls can also be placed on as part of an HD application using a component called T-viewport 3D. And so in the 3D controls, we have a T-dummy, and T-dummy can be used as a container for other 3D objects. That way, when you want to do rotations or set the position, you can set it to the dummy, and everything that's inside of it will be positioned and rotated accordingly. There's T-camera for looking at a 3D scene, and you can have multiple T-cameras that are manipulated and moved around. You can put lights, multiple lights, and lights either are spotlights, directional lights, or they're point lights shining in all directions. There's a bunch of T-shape 3D, T-cone, T-cube, T-sphere. There's a T-text 3D if you want to put 3D texture, a 3D text in your application. And again, you can mix HD and 3D together. Now, if you're going to use a 3D, you'll need a GPU. And if you use a viewport 3D inside of an HD application, it requires a GPU. But again, the computers in the last 7 to 10 years on PCs and Macintoshes and iOS devices and Android devices, they're all coming with GPUs these days. So you shouldn't have a problem. Usually on Windows, we tell people, unless you have a very old graphics card, it'll probably work. The other way to know on Windows is if there's a DirectX 9 driver for your graphics chip or graphics card or PC, maybe if you're using the Intel integrated graphics chip on your motherboard, that has a GPU in it. The great thing about Firemonkey and its coordinate system is that if you write, and components, if you write to Firemonkey, then we map it underneath to the underlying operating system platforms and hardware that you run on. So the way it works is you write to Firemonkey, your C++ application. If you're running on Windows, we'll use Direct 3D for your 3D applications. On Macintosh, we'll use OpenGL, and on iOS for Delphi now, but in future versions of our C++ compilers, we'll support iOS and Android. Then we use OpenGL ES. And so wherever we go in the future with our C++ compilers to different platforms, if there's an HD and a 3D graphics rendering system and a GPU, then your Firemonkey application will just work. You'll just recompile it using our compilers for those target platforms. 3D Firemonkey requires a GPU, and the GPU will do everything related to doing transformations and visualizations of the application, the lighting, textures, animation. It's all done by the hardware. So you can just send off, call the components, lay out your application, call the methods, and underneath Firemonkey will send everything off to the underlying 3D system, which will pass it and render it along using the GPU. And again, as I mentioned, you can put 3D components inside of a viewport 3D on an HD application. So on Windows, it uses Direct 3D, and on Mac, it uses OpenGL. The coordinate system for 3D is Firemonkey has its own coordinate system that then, in the runtime, gets translated to whatever platform you're running on, what its coordinate system are. People have asked me questions, well, gee, DirectX and OpenGL have a different orientation for the z-axis and the y-axis, for example. Just program to Firemonkey. It does the right thing on the right platform underneath for you. That way you can write one set of code. You don't have to spend all your time doing transformations. So in Firemonkey 3D, the positions of X, Y, and Z are relative to the parent or the form that you're putting your 3D objects into. So positive X starts from the center of the parent, whatever the parent is. For example, you put a 3D object into a T-layer 3D inside of a form 3D. That 3D object would then be, its parent would be T-layer 3D. But in any case, positive X goes to the right of the center of the parent. Positive Y goes below or down from the center of the parent. And positive Z goes into or away from the user into the screen of the parent. So X, Y, Z, it's all relative. It's relative to the center. And rotation angle, there's a rotation angle property. It rotates around the center of the axis of the X, Y, and Z axis. So there's a rotation X, rotation Y, and rotation Z property. And you can set the number of degrees of rotation for each of those. And again, for X, Y, and Z, those are T-position component, T-position 3D component, property. And those are floating point, a single precision floating point values. That way, we can map to whatever the underlying coordinate system and pixel system that might be available on platforms today with Windows and Mac and platforms into the future. There are lots of different objects, as I mentioned, in the hierarchy with shapes and components. There's also 2D objects that are extruded. They have a depth property 3D. So, for example, there's T-text in HD. There's T-text 3D in Firemonkey 3D. And the extruded objects have three sides. They have a front, they have a shaft, and they have a back. And you can set the color and or texture for each of those parts of a 3D object. So, for example, in HD, there's T-path. In 3D, there's a T-path 3D. In HD, there's T-text. In 3D, there's T-text 3D. And also for things like images, there's T-image, and then there's T-image 3D for 3D space. Here's what the tool palette looks like of components. Here's all the components you can drag and drop into your Windows and Mac C++ application. And there's the layers, the T-layer 3D, a T-layout 3D as well for setting up the positioning of components. And we use these layers to allow you to put 2D components inside of a 3D application. And then for manipulating the scene, we have T-camera. You can put the camera and move it around. A 3D form comes with something called a design camera. And there's a property called Use Design Camera that's turned on by default. You can turn it off and then drop a T-camera inside of your form. And then you can manipulate what the view is of that 3D form by moving the camera and its rotation. You can have multiple cameras and you can enable and disable them. You can have multiple lights, so you can light up different parts of your scene, of your 3D scene, and you can have multiple cameras. Think, movies and television where you have a 3-camera shoot, or an action scene in a movie, you've got 26 cameras. You just turn them on. And you can position the cameras so that you would just turn on and off cameras and you get different views of your 3D scene. Or you can have one camera and you can move the camera, move its position and its rotation angle to take a look at the scene flying by, or maybe you're building a 3D view of a building and you want to fly through the building and move the camera around. We also have a T-model 3D component that can load up DAE, OBJ, or ASC model files. DAE or Collada files, and OBJ is the pretty standard used in products like Maya and such. So you can load up 3D models and use this T-model 3D component. We also have an example that ships where we show you how to import a 3D Studio or 3ds file. And we're looking at supporting additional model file formats in the future. So in the course book, we're going to get to demos here in a quick moment, but in the course book, I talk about cameras. And again, here's this property called Use Design Camera that's part of a 3D form, so that we give you a view of whatever you put on your form. But again, you can drop your own cameras in and turn off Use Design Camera. If you don't have a camera and you run a 3D application, then there won't be anything to see because there's nothing showing the user interface of your application. But by default, when you say File New 3D Application, Use Design Camera will be turned on. it sits at XY00, and it's the Z axis is angled slightly so that you can look at the scene and display it. Again, position 00 is top left corner in 2D, and 3D it's center of whatever the object is that's containing these other 3D objects. And as the Z-axis is greater than it's moving away from the viewer, then the rendered size will appear smaller. So, if you take a sphere and send it off in the distance, it should get smaller, like planets as you move away from a planet. If you move it negative, then it comes closer, so its rendered size gets larger. And so in here, there's all sorts of information about materials and lighting and these things. For the color of materials, including the surface of your different 3D shapes, the emissive color, if you set that value, then the surface of the 3D object will emit its own light or glow with whatever color. If you set it to null, then it doesn't glow, and you need to put a light in it for it to be seen. Ambient colors is that base color to surfaces, and again, it depends on if you put a light inside of it or not. So you may have the sun or ambient light somewhere in the room or in the scene. Diffuse color interacts directly with the light, including the angle. So if you don't have a light, diffuse doesn't mean anything. If you put a light, then it's there. And specular color simulates a glossy surface by doing a little bit of manipulation of light that's bouncing off or sort of off in the distance and comes in. All right, and again, you can mix 2D and 3D. You can put a T viewport 3D inside of an HD application. Let's just take a look. Let's take a look at building an application. So we say File, New, Firemonkey 3D Application C++ Builder. Again, I've added these into my File, New. I talk about that in Lesson 3 on the ID. Otherwise, they'll be in File, New, Other, C++ Project, and you'll see Firemonkey 3D Application here. So we'll create a 3D application, and here's my main program, which is going to create a form, which is of type tform 3D. And in the code, we don't have anything yet, but we'll start placing objects into it. Here's our main form. It's a 3D form. And down here is that property use design camera, which is on by true. We need that so that if we put, for example, 3D objects, here's a sphere. The sphere starts with a height, width, and depth of 1. We can use the object inspector to make the sphere bigger, set its height, its depth, and its width to 5, for example. We can set its material, the emissive color. Let's just set it so we don't need a light for now. There's a violet, spring green, or whatever it might be. You can set it to null and then and set other colors on it. Set the other properties. So, for example, the diffuse color, the ambient color to something else. And then we can put a light in it. So let's put a light. And now the light is sitting underneath. We can move the position of the light. Here's the light underneath. We can set the light's position, and we can move the light around as well. We can say who the light points to. Let's set its position to -5 on the z-axis. And we have the property for the light type. It's a directional light, or it might be a spotlight. And again, it's very vague. You can kind of see it as I move the light over the object. It kind of lights up. That's with the spotlight. And then we can also set a point light so it shines light in all directions. So again, as I move around and I light up the object, that we get its whatever that color is I chose for the sphere. And again, we can make it a highly directional light as well. So it's just pointing at it. And then we can run the application. It just runs on Windows. And we've got a lighted sphere. And we can put multiple lights on it. Let's put a spotlight on it here, and we can put another light and have it lit up further, so we can do all sorts of lighting effects, make a brighter spot, for example, in this corner, deal with it. So multiple lights. Now again, I'm using the design camera, so if I turn that off and hit run, then we don't have anything because we don't have a camera. So I can put a T camera down, and we can say have that camera, for example, put its position somewhere. We could also have it look at an object, so set its target property. So, for example, have its target be the sphere. We'll compile and run it. Now we've got this sphere, and the camera is closer to it. So let's set the position to -20, for example. Now the sphere is smaller, it's further away, and we could build a user interface that moves the position of the camera. Let's go and put a T-layer 3D, and let's move it to -5. And inside of this layer 3D, we could put a T track bar. Let's set its position to 0 and 10. And we'll set its value to something like 5. And then we could have that track bar on change go and set the position of the camera. For example, we could say camera 1, its position Z, equal to the track bar 1, its value property. So we could use this little layer here and set and use that track bar and maybe buttons or other things to manipulate the camera and where it's positioned. Now, as I mentioned, we could also create a C++ HD application and put components down like a button and a track bar. And then to put 3D objects into a 2D or HD application, we put a viewport 3D area. So let's make this this part of the application. And then inside of, we can put a sphere and set its width and height and depth to something bigger again. And set its height to 5 and its depth to 5. And set its, let's have this one be an emissive color, so let's make it a tomato. These little grabbers, I forgot to mention those, are used for rotating the position, the X, Y, and Z position of the object. So down here in the object inspector, if I look at the position, you'll see as I grab them that the position value of the rotation angle, in this case, is changing. So as I manipulate these little grabbers, the rotation angle value is changing down here inside of the object inspector. And this little corner object we can use to change the size, the width, and depth. We grab each of the corners of these, and it changes the underlying height, depth, and width of the sphere. So you can either do it in code, you can do it in the object inspector, or you can grab, and all these objects have the little handles that you can grab. So T-cone, here's a 3D cone. Let's move it down here. And we can put a cylinder as well. And then when we make the cylinder larger, it'll look more like a cylinder. We can rotate it around. And again, Viewport 3D has a design camera. So that's turned on by default. But we can also place a T camera in the viewport and then turn off the design time camera. So if we run this application, we've got our button and our track bar. So let's start the camera's position at -5, and we can let's set it further away, and then we can use the track bar and set its value, its min and max value to be, let's make this -30, or make it 30, and the minimum be 0, so 0. And then on change, we can set the camera, we can set its position Z value equal to the track bar value, and let's set it to minus of that. So we can change the camera angle to be a larger negative, so as the -Z value of the camera, as the camera pulls back, the look is as if the objects are getting smaller and further away. But it just turns out that it's the camera that's moving. The objects are the same. They're being re-rendered by the relationship of the camera inside of the viewport and these 3D objects. So there's a HD application with 3D viewport put in it with 3D objects, or building a 3D application. Let me show you an example application that Anders Olsen built. There's two of them actually for C++. One of them is a math visualization example. And what it does is it has a control panel. Here's a layer 3D that we place a bunch of HD components, like these buttons, for example, and so on. And we've got some speed buttons and an arc dialer and a track bar to use for rotating and zooming in and out the camera. He's got a light in a 3D part of the interface with a layout 3D. He's got grid lines for the X, Y, and Z axis, a mesh object that is going to contain calculated values of X, Y, and Z, and triangles to display a surface of the application. That's all placed in the component called the data of a mesh. And inside of the data of a mesh, we've got points, textures, and triangles. And he's got a text 3D, which is a just text label that has a text property called select a function to graph. And that text 3D can have a material or color. He's just got the ambient and emissive colors set to white. He's got the fill mode to solid. The other option would be wireframe, but since it's going to be text string, we leave it solid. And we've got a light that's a point light that's sending light in all directions to light the surface of the graph. In the code, there's a set of functions that he pre-builds in of these trigonometric functions. And to avoid a division by 0, we'll set a very small number, 1e to the minus 20th, or that way we can avoid divide by 0 if we pass it values of x and z. And then he's got a generate mesh function. And all the source code for this is available. The link is in the course book. He generates for the x and z axis from minus 30 to plus 30, and then uses these functions that are built in to calculate the y value to generate the mesh. So here's 2 while loops that are iterating through negative x and negative z to positive x and positive z, so minus 30 to plus 30, and then calculating the y values based on the functions that are provided. For the mesh component, sets the vertex buffer, which is a low-level buffer inside of the data of the mesh. He sets the vertices of the points for x and y and z that form the triangle. For whatever the value of y is, he maps a color texture as a bitmap to color the trig function. And the bitmap is simply a single pixel wide bitmap from black to white and the color of the spectrum in between. So he calculates the points, he maps the colors, and then he sets the triangles for those points, and then simply sends it off to the GPU. The mesh will send it off to the GPU. It will generate the triangles, map the texture for the triangles, and the points where those triangles are on the display. And then he's got some buttons here for generating the mesh and doing rotation, selecting the different functions. And then if the grid is on or off, there's checkboxes for that. And also this arc dial will rotate the z-axis. And we can use the mouse to also zoom in and out, and the mouse wheel to move the camera in and out. And he's got a timer so that you can start rotation until you click the button off. So let's take a look at this on 32-bit Windows with C++ first. So here's that text 3D. We've got grid lines using T-grid, and you set the grid line color to do the X, Y, and Z axis. We can turn off the grids if we want. And then the buttons are tied to the different functions that are pre-built in. So here's one that is the sine of x squared plus z squared divided by x squared plus z squared. And remember, we're going from minus 30 to 30 for x and z. So when x is 0 and y is 0, that would be a division by 0. But Anders has code to check for that, and he substitutes the value epsilon, which is 1e to the minus 20, which gets us this top point at the top of the grid, or of this mesh, rather than getting an exception or having it sending values way up high. And so we can use these buttons to rotate around. We can use the arc dialer to rotate the other axis, and we can use the track bar to zoom out or zoom in. Again, that's just moving the camera. Now, some of you are seeing, when you're seeing in GoToWebinar, you're seeing GoToWebinar grab the screen I forget how many frames per second, but it's not the number of frames per second that I can run on my computers. So we can go inside the graph. So what you're seeing is, I'm going really fast. It runs very fast on the GPU. What you're seeing is GoToWebinar grabbing screens, frames at a time. So if you download the code, it's all available in Code Central, and I give you the links in the course book. You'll see all of this in action on your own GPU, and it'll be very fast. Again, all of this runs on Macintosh as well, so we can go and add a platform, add Mac OS X, and make sure we have the right remote profile selected. So here's my Mac. I'm talking to my OS X machine through port 64211. So we'll compile and let's see. Oh, okay. Now what it's doing is it's updating the cache. Hold on. Let me stop and go back and set the right. I forgot to hit. Let's select the right profile, and yes, it can connect to it. Say OK. Assign it. Sorry. Let's assign this one. All right. And now we can run this, compile and run this on Macintosh. So it's compiling this code. Again, all the commands are being sent off to the GPU ultimately for this generate mesh function. And there it goes. So now it's going to send it off to the Macintosh. And there goes the debug information, some runtime library dilibs. And here we go. And here's our C++ application running on the Mac. And again, we can rotate and look at the different functions and zoom in and out by using the trackbar, just moving the camera. So there's a little more complex application. Let me show you one other application that, again, I give you the links to. This is to show you the speed and power of Firemonkey. This one is a wave interaction example that Anders has built. And what this is going to do is this will generate meshes on the fly over and over and over again and send them off to the GPU. So if we look at the source code, in this case, we've got, again, we create the form. It's got a panel with track bars on it for setting the amplitude and velocity of the wave. And then he's got a function called generate wave, and inside of there it'll generate the wave over a -30 to +30. So think of this as if you had a vat of water and you dropped a stone in one corner or another corner, and then the ripple effects of the wave. But it's the same code as we did in the math function. We're just taking a function of the wave interaction formula, and then we're setting the points, setting the texture, and setting the triangles, and then just texturing it and let the GPU do the updates. So the user interface has this layer 3D, which has a group box, which has checkbox and labels inside of it, and a track bar. So track bar for X, Y position, amplitude, and velocity. So let's run this example. And again, the full source code is available. So here's our vat of water. We can drop a pebble somewhere in a position, like in the corner over here, and it starts doing the interaction. We can change the amplitude. We can change the wavelength and the velocity of it. We can also rotate around by clicking on the mouse. And we can drop another pebble in another side, and another pebble in the other corner, or wherever the position is for the center. Again, it's going to look a little jerky on GoToWebinar because it's grabbing frames. But we can really change the velocity and wavelength. And on a GPU-powered machine, it's just pulsing wave interactions of these waves slamming into each other. And it's generating the meshes on the fly and sending them off to the GPU, and it's rendering them as fast as it can. Right? And I can rotate it around. So If you want to see a complex interaction where the GPU is working really hard, the next thing you'll hear is the fan coming on inside of your computer as the GPU works really hard. All right, so let me switch here. Again, I'll give you all of this in the lesson book, and there's, of course, more information to go on. Here's the links, and again, those are in the workbooks, or you can just search on EDN or Google for visualizing mathematical functions, the C++ version, or the visualizing wave interference using Firemonkey, C++. HD and 3D working together, or 3D applications running on Windows and Macintosh using Firemonkey. And then I've got links to other sources and demos. Thank you for joining me for creating Firemonkey 3D applications for Windows and Mac. It's very easy to do. Firemonkey 3D C++ project, or an HD project with a 3D viewport. And next week we'll be covering image and animation effects with Firemonkey for Windows and Mac or C++. So see you next Thursday, same time, same URL. Take care, everyone, and we'll see you next week.